you should have marked the location that was just below where the ramp was lined up with the table. So the idea is this represents where the ramp was, but at the table's height. And then you had a group of dents on the paper where you release the ball by itself. And then hopefully you had a real collision, not just a head-on collision. Because if you had a head-on collision, your data is all garbage. You wanted a glancing collision, so they would go off in two different directions. And you had a collection of dots on one side and a collection of dots on the other. Now, you're supposed to hand this to somebody in the room for your table who would take measurements. And that measurement started with drawing a line to the middle of that set of dots. This represents your range and group, but this was going to be used to calculate the initial velocity. You would find the time from your height. And although I shouldn't have to do this, I have found it necessary. So you have your height from your table. That tells you your time. The truth is, the time is the same for all the projectiles. We could probably just compare the distances and do the same thing. But we're trying to actually compare momentum. You should get the time. Then you put the target ball in place, did a glancing collision, and produced two other groups. This side, velocity on the right, this side, velocity on the left. You should probably kept track of which was the target ball and which was the collision ball, so you know which one went which direction, but it really won't make much of a difference, because if you did this lab correctly, the mass of the two balls was the same. So if you use the two black plastic marbles, they're the same mass. The two metal marbles are the same mass, and two of the glass marbles will be the same mass. Now, the whole idea here is that you're trying to demonstrate momentum conservation. You're trying to show that the momentum initially is equal to the momentum after the collision. But this is a two-dimensional collision. And because it's two-dimensional, this vector equation has to be broken up into things that you can analyze, because you can only analyze one-dimensional collisions. So you'll need to break this up into the x direction and the y direction. So I'm thinking the x direction is this way and the y direction is that way. If you're of similar mind to me, then there was no momentum in the x direction before the collision, and there was only a momentum in the y direction. And that's what I would set this up for. Now you have your angle that you measured, so you could find out how much of this velocity was in the y direction and how much of this velocity was in the x direction. And you could find out how much of this velocity was in the y direction and how much of this velocity was in the x direction. So that would produce, say, mv left in the x direction and mv right in the x direction. Oops, not the v. Of course, one's in the positive direction, one's in the negative direction. And then you could have calculate mv left in the y direction plus mv right in the y direction. Since for all of your trials, the marbles had the same mass, I think you don't have to worry about what the mass of the marbles were. If they were different masses, you would. I would argue that you probably don't have to worry about the velocities, since all the times were the same. You could probably convince me of just comparing the directions. That would be fine too. You understand what I'm saying? You could convince me. If you want to be able to do it that way without having to calculate the times, all you would have to do to convince me is have a paragraph made up of maybe one or two sentences in your explanation. But if you don't know what I'm talking about, then I guess you're going to have to do all the calculations to find the velocities. But if you do, you can make a reasonable argument that you only have to compare the distances. Now, here's where things are going to get a little bit dicey, and I want to be really clear. You're just making a comparison. You're seeing if these add up to be 0. And you're seeing if these add up to match the initial. You're seeing if they are equal and if they equal 0. But they're very unlikely to be an exact match. So how do you show if you're within a reasonable vicinity of the answer? Well, this is why you needed your picture. Because if we look at just one of these, there is a variance in the x direction. In fact, the actual marble landed in the x direction somewhere between these two distances. And in the y direction, it landed somewhere between these two distances. Right? You just did the average. You actually don't know which of these spots goes with any of these spots. You don't really know. You have a collection of averages. So the truth of what I'd like you to do is find the amount of experimental error from your data. You have scale because you have this size. It was written down by somebody. So looking at your picture, you could probably figure out plus or minus what? Each one of these is plus or minus a small amount. And that's true even here, right? So your job is to find out how much error there is and see if you are equal to 0 or equal to the original momentum within your reasonable error. Does everybody understand? That's what I want for this lab. You're going to do it 3 times, one for each one of the pictures you drew. Let me just give you a couple of points about what I want to see in your write-up. Because first, people who get D's and F's in this class, it's because you don't turn your work in. And once you get towards, to a certain point in the semester, it's hard to go back and do that work again. Labs are a big part of that. I give you lots of time on them. I give you like a week. So you can't ever say you don't have enough time to write up your labs. You can't say you forgot to write up your lab. But here's what I want in your lab. I read the end of the lab first. You should know I just scroll right to the bottom and see your results. And then I go back and read what you wrote earlier. So I'm looking for something first. And I'll say what it is. I am looking for you to answer the purpose. The purpose of the lab is going to say something. At the very end of the lab, after you have all of your data in front of you, I'm looking for you to answer that purpose. Many of you skip that part, which is, if it were up to me, I would just give you a 0. I usually give you less points, not 0, but you just skip that part. You just think that the analysis is what I want. No, I want you to interpret the analysis. So the purpose of the lab was to demonstrate conservation of momentum for a 2-dimensional collision. I should see a derivation for conservation of momentum. We did it in class last semester. It started with saying the force of 1 on 2 was equal to minus the force of 2 on 1. Saying it was a vector. We started with Newton's third law. We multiplied both sides by t and showed that the momentum change of object 1 was equal and opposite to the momentum change of object 2. Do you remember this derivation? If not, I just did it in first and second period. The video was just posted today. Just watch their video. It's the same thing. I want you to demonstrate where conservation of momentum comes from. Show that it stems directly from Newton's third law. That's your background. I would like you to give me a quick overview of how you took your data, like always. Then I want you to show me these measurements and what you did with them. That's your analysis. At the end, you need to say whether your data supports conservation of momentum or not. I'm going to be looking for this kind of comparison. I mean, you could do it this way. See if those two things are equal within their margin of error. And similarly here, add those up and see if they're equal within their margin of error. If they are, you proved it. Or at least your data supports it. If they aren't, you didn't. What you guys fail to understand, I think, is that although I want you to do a good job and I want you to be careful, I want you to take good measurements, if you don't prove it, then you don't prove it. If everything about your lab supports that you knew what you were attempting to do, and in the end, you were unable to prove something, then you just need to say that. And that's what I'm looking for. I'm looking for you to interpret your data. You don't get marked off if you don't prove conservation of momentum. You get marked off if you say, yes, I proved conservation of momentum, but you clearly didn't. Or you don't have data that supports it, or you didn't actually do the calculation correctly. That's where you get marked off. Does that make sense? So if you prove it, great. If you don't, fine. With the plastic marbles, it's harder to prove it. So we'll see how you did. With the steel marbles, it's easier to prove it. All right? Any question about the lab? We'll be doing a week, so next Tuesday. All right? Yeah. You'll have to take a set of data. You can do it any time because I'm going to set up a ramp at the back of the class, and then you can use the remaining 2 pieces of data from your group members. Does that make sense? Okay. There's going to be a bunch of people coming, 2 people coming in tomorrow morning to do it. So if you can come in tomorrow morning around 8, there'll be a meeting going on in here. It's not easy. It's not hard to do. The paper's in the front, and you just drop the balls. Just talk to your group members about how you did it, but it's really super simple. Let's talk about the part that's less fun. In order for us to have a conversation about rotational motion, we're going to have to make some comparisons between translational motion and rotational motion. You already have a full kinematics workup of translational motion. You already know things like delta x, v naught, v, a, and t, and you know what all of those things mean. For every one of those in translational motion, and from this point forward, translational motion means objects that are changing location. That is translational motion. Objects that are changing location. That's what we did all first semester, was translational motion. Rotational motion is for objects that are changing direction. They're changing their orientation in space. So an object can be doing both at the same time. You throw a frisbee, it has got rotational motion and translational motion. Now, rotational motion has all the same things. Something can spin around a couple of times. We would say that that's delta theta. It's angular displacement. Put the word angular in front of all of those words, and you now have the rotational version of the word. So we already talked about this first semester when we talked about circular motion, that there is angular velocity. And we could have an initial angular velocity and a final angular velocity. It's not a surprise what we're going to use next. If we're using Greek letters for everything here, then probably lowercase alpha will be the appropriate letter to use for angular acceleration. And of course, time isn't angular or translational. Time is just something. Something to make sure everything doesn't happen at once. For all of these, the units are going to be largely the same. So this will be per second. This will be per second squared. But then you have an option, right? We have rotations, radians. Heck, you could have degrees, which means our omega could be in radians per second, degrees per second, rotations per second. And angular acceleration could be in rotations per second, radians per second, degrees per second. I'm sorry, radians per second squared, rotations per second squared, and degrees per second squared. These are all different ways of measuring angular motion. Now, there's a direct comparison here. Hopefully, it's enough of a comparison where you don't have to work that hard at what's going to come next. Because you already have motion equations. I don't believe we have to rederive all of these like we did. Do you realize that for something that's going to have angular acceleration, it could start at an initial velocity, accelerate, and change its velocity? It would just mean taking this and translating it into angular values. They're already on your equation sheet. So for every Galilean motion equation that we did for translational motion, there is a rotational motion counterpart. So I hate writing them all out because I think it insults you a little bit. But I also know that I can say, can't you guys do it on your own? And you won't. So there, we're left with it. These are the ones that are on your equation sheet, I believe. Thank you, whoever's moving that around. Stop playing with my toys. See, we just won't do this anymore. You guys can't handle it. So the motion equations, but all for angular stuff. Now, this whole unit's on rotational motion. But don't forget that we still have things about force that have to do with angular motion and circular motion. We're not going to stop not thinking about those things. If something's spinning in a circle, then we will probably have some triple motion. Let's do an example question. You and your friends go to an amusement park and you all get on the carousel, each one of you choosing a different horse to sit on. All the horses are evenly spaced 1 meter apart, and the first horse is 1 meter from the center. So 1 meter, 1 meter, 1 meter. That good? That means that the horse on the outer edge is 3 meters from the center. All good? Yes? All right. Everybody gets on a horse, except for one of your friends who's going to sit out here and take pictures. So the ride starts from rest, and in 10 seconds, it gets to its operating speed. When it's at its operating speed, your friends pass you once every 4 seconds. Everybody hear all the details? I just gave you 3 motion variables. I want to know the angular acceleration and the angular displacement. How many rotations did the ride make getting up to speed, and what angular acceleration did it experience? Now, we're doing this for the first time, and I'm just getting started, but we are doing kinematics. So because we're doing kinematics, we should probably start here. You and your friends get on a ride. The ride starts from rest and gets up to full speed in 10 seconds. When it's at full speed, your friends pass you once every 4 seconds. I gave you all of that information. And then I asked for the angular acceleration and the displacement. I think the hardest part about this stuff is knowing what you've been given and how to use it. But remember, this is something that's always going to be in rotations, radians, or degrees. These are always going to be in the per second. Oh my God. You guys can't be trusted. This is going to be in radians per second squared, rotations per second squared, degrees per second squared. And this is the only one that's going to be by itself with just seconds. Now your job is to figure out what to do with the information you've been given. So I'll give you a moment to see if you can work this problem out. I didn't specify the units I wanted my answer in, so you can use whatever units you'd like. Try it. Very familiar to original kinematics. So let's go with the easy one, the one that groups these four things together. I probably would have picked omega equals alpha t plus omega naught. And we're solving for alpha. So I got 1/4 equals alpha times 10 plus 0. So solve this for alpha. I get 1/40th rotations per second squared. And yeah, you can make that a decimal if you want. I don't care. Now I also need delta theta. So I need a relationship. I could use alpha now, so I can use almost any relationship that has delta theta in it. But remember my rules from last year. I try to suggest to you guys that you only use given information when you can. So I'm going to use delta theta equals 1/2 omega plus omega naught times t. This uses only the given information. And let's see, 1/2, 1/4 plus 0 times 10. So that looks like 5/4 rotations. That's it. This is the kinematic stuff. But it isn't it. We know other things. So let's talk about the other things we know. For example, when it's at full speed, how fast is each kid actually moving? What's each kid's tangential velocity? Remember the difference? And do you remember how to get this? Yeah, who remembers how to go from an angular value to a linear value? Okay, I got one of you. Can you tell me? Yep. The tangential value equals the angular value times how far away from the center they are, the radius. But, big caveat, you can only use this if this is in radians. So if you want to use this, this is where the units matter. You'd have to convert it to radians. Now that we're into this unit, let's add something here, because this is true regardless of whether we're talking about velocity or acceleration or displacement. You can use this for all of them. If I need the tangential acceleration, then I can use the angular acceleration. But it's still true, all of these have to be in radians. They all have to be in radians. That's why for where you sit on the horse, or I'm sorry, where you sit on the carousel, your answers are different because the linear values for each of the kids is different. The further away from the center they go, the faster they're going, the faster they accelerate, the bigger the distances that they travel. But remember, all those have to be in radians. So if we want to actually find the velocity of those kids, I need to take the angular speed and convert to radians. I'm concerned you guys don't remember how to do this, even though we did it just a little while ago. So let's practice. I want to take my 1 rotation every 4 seconds and convert it to radians per second. Now look, I know that this is just multiplying or dividing by 2 pi, but it gets more and more complicated as we start adding other units here. So I use unit multipliers. I would strongly encourage you to do so. It takes you an extra second. You have to write some stuff out. But you look silly when you get these wrong. And then you give me that baleful look, well, I divided instead of multiplied. No, you don't understand what you're doing. It makes you look like you don't understand things. So let's just write it out. We need radians. We don't want rotations. So you put what you're trying to cancel out in the opposite side of the line. And pick where you want to go. So I don't want to go to degrees. I want to go to radians. So put radians there. Now you have to remember your fact, your conversion fact. There are 2 pi radians in every 1 rotation. So now I work this out. Take that 3.14159 divided by 2 and get 1.57 radians per second. Okay. So I want to figure out how fast the kids are going. Well, their tangential velocity is going to be 1.57 radians per second times either 1 meter, 2 meters, or 3 meters, depending on which kid you wanted. So not a big deal. 1.57 meters per second for the kid that's on the inside. 3.14 meters per second for the kid in the middle. And 4.71 meters per second for the kid on the end. And this is a lot of bean counting. Like I said, it's just kinematics. But can't get to the other stuff until you got your kinematics down. Again, I only tend to talk about kinematics for a little bit. Today and part of tomorrow. You should practice the kinematics I've posted. Well, I will post when I sit down next. Canvas was doing some funky things earlier this morning. Now, there are other questions here, like what was the linear acceleration of the outside kid? That's a great question. You should be able to do it. You have 2 different ways to do it. For example, you've got their speed. You could just use v equals at plus v naught and figure out what their linear acceleration was. They went from 0 to 4.71 meters per second in 10 seconds. Or, since you have the angular acceleration here, angular acceleration here, you could calculate the tangential acceleration by taking the angular acceleration and multiplying by 3 meters. But you couldn't put 1/40th in there. You would have to convert to radians first. Okay. I'm expecting we're going to have a quiz on this in a couple of days. I'm going to expect that you guys are proficient. And I'm going to ask questions just like this where you're bouncing back and forth between linear and angular. And look, there's no reason not to ask what the centripetal acceleration of the kid in the middle is. All right? It's all part of the stuff. So I'm going to go ahead and end there because I think we're just about done. No, I have 6 minutes. I have 1 minute. Sorry.